Have you ever played with magnets? They're pretty neat. Magnets create an invisible force around them called a magnetic field. This field is what allows magnets to attract or repel other magnets. Think of it like an invisible area of influence. Now, imagine you have a loop of wire and you move a magnet near it. Something amazing happens. Electricity starts flowing through the wire. This magical phenomenon is called electromagnetic induction, and it's all thanks to magnetic flux. Magnetic flux is a way to measure how much of this magnetic field passes through a specific area, like our loop of wire. It's like counting how many invisible magnetic lines go through the loop. The more lines, the stronger the magnetic flux. The stronger the magnetic flux, the more electricity we can generate. It's a fundamental concept that makes generators, transformers, and even electric motors work. Scientists use a simple formula to calculate magnetic flux. PHB = BA cost. Don't worry, it's not as complicated as it looks. Let's break it down. PHB represents magnetic flux, measured in a unit called Webers, WB. It's our way of quantifying this invisible magnetic field. B stands for the magnetic field strength, measured in Tesla's T. The stronger the magnet, the higher the value of B. A represents the area of the surface through which the magnetic field is passing. Think of it like the size of our loop of wire. The bigger the area, the more magnetic field lines can pass through. Cost is a bit trickier. It represents the angle between the magnetic field lines and the surface. We'll talk more about this in the next section. Remember that cost term in our formula? It's there to tell us that the angle between the magnetic field and the surface is important. Imagine you're holding a hoop and I'm throwing tennis balls at it. If you hold the hoop straight on, more tennis balls will pass through, right? That's like having the magnetic field lines hitting the surface head-on. Theta = 0 degrees. The cos 0 degrees is 1, so the magnetic flux is at its maximum. Now, if you tilt the hoop, fewer tennis balls will make it through. Similarly, if the magnetic field lines hit the surface at an angle, theta > 0 degrees, the magnetic flux decreases. The smaller the angle, the less flux we get. If the magnetic field is parallel to the surface, theta = 90 degrees, no field lines pass through the surface, and the magnetic flux is 0. It's like holding the hoop sideways. No tennis balls are getting through. Magnetic flux is more than just a cool concept, it's the backbone of many technologies we use every day. Generators. These amazing machines convert mechanical energy into electrical energy using, you guessed it, magnetic flux. By spinning a coil of wire inside a magnetic field, we change the magnetic flux through the coil, generating electricity. Transformers. These handy devices allow us to increase or decrease the voltage of alternating current, AC. They work by using magnetic flux to transfer energy between two or more coils of wire without any physical contact. Magnetic resonance imaging, MRI. This life-saving medical technology uses strong magnetic fields and radio waves to create detailed images of the inside of our bodies. By measuring how different tissues interact with the magnetic fields, doctors can diagnose and monitor a wide range of medical conditions. So, next time you turn on a light, charge your phone, or get an MRI scan, remember magnetic flux. It's a fundamental principle of electromagnetism that makes our modern world possible.